RockTrue Science is a cross-cultural response to the lack of diversity in STEM fields. STEM stands for science, technology, engineering, and mathematics. RockTrue Science is designed to serve the intellectual need of fallen man while serving the desire for interdependence to better understand our physical world while still pursuing spiritual growth. RockTrue Science seeks to inspire, enlighten, and highlight upcoming and established local and international kings and queens of STEM fields while promoting Black consciousness and awareness of who we are and to whom we belong. Welcome, welcome.
Hello, hello.
Good evening. It's evening, right? Kind of 6 o'clock counts, right?
Right.
Everything in order. That's the one I need. I need one of these. All right. Oh yeah, I'm excited. Today is experiment day. So I found another experiment. So we are still doing the 10 hedgehog, as you can see, but we're also going to be electrolyzing water.
I was like, okay, that's gonna be interesting.
Yeah, basically all it's doing is turning water back into its gaseous component. So taking H2O and making it gas, hydrogen, and gas oxygen.
Oh,
And with that being said, of course, we're going to start our journey through the periodic table. And it's got so many twists and turns. But we're starting off with our very simple friend, hydrogen. And that's way up in the top left corner. If you see a periodic table, a standard periodic table, there's always going to be in the top left corner because of its reactivity. So everything in that group is extremely reactive with water. And it's funny that hydrogen is reactive with water when it's the component of water. Go figure. And actually everything under it, the lithium, sodium, potassium, rubidium, cesium, and francium, they all actually form bonds with hydrogen. So you get lithium hydride, sodium hydride, potassium hydride, rubidium, and all the way down. But the rubidium, cesium, and francium, you'll probably see less of those in actual compounds because of how reactive they are. They're extremely unstable. If you have any type of familiarity with hydrogen and hydrogen gas, you know hydrogen gas is extremely flammable, it's extremely reactive, and it is very, very hard to I would say maintain without it doing stuff. So that's why I'm so glad that we get to start with hydrogen and talking about all of this many different properties and what it can do. Of course, you're mostly familiar with it as water. Well, in water, but it is also the most abundant element on Earth. So it accounts for about 75% of the Earth's mass. So that's a lot. So because water is obviously 70% of the Earth's surface. So with hydrogen being 2 of the atoms in water, you can imagine why it's the most abundant element overall. Greetings, Ty, and welcome.
hello, good evening, sir.
So here, this is basically what all the elements look like in the elemental table. Will not look like specifically, not, you're not gonna look at it and it looks like this. But this is all the information that each individual square has in the periodic table. So the physical state that it's talking about here is its natural state at 20 degrees Celsius or 68 degrees Fahrenheit. So sometimes in science you'll see something called at STP, and that's standard temperature and pressure. And standard temperature and pressure for scientists is a lot different for the general public. So a barometric pressure of 0 degrees, not 0 degrees, 0 millimeters of mercury. So that's usually how they would measure the barometric pressure. And that's a standard pressure, meaning that there's no pressure. No pressure, no pressure. And then the standard temperature is normally room temperature, so it's usually roughly about 70 degrees Fahrenheit. So that's a little bit more precise, the 68 degrees Fahrenheit, and or that's where they kind of gauge it for the periodic table. And then also the standard no, that was it, standard temperature and pressure. So for the most part, most experiments are usually attempted to be conducted at STP, because that's usually how they make all of the standards and any type of information that they want to gather for a particular element. They do it at standard temperature and pressure, so that is very reproducible and duplicatable, as we talked about with the scientific method. That is extremely important for things to be established as a scientific fact, is that it's reproducible, and someone can reproduce the experiment and get the same results, and that's how you do that. Did you have a question?
No, I'm following. I'm following. I'm doing good. Doing good so far.
And bring the picture back up, because there's some other information on there I'll cover. Oh, the first one with just hydrogen. Yes. So the atomic number always refers to the number of protons. And so I'll explain a little bit later why that's the case. But the atomic number is the number of protons, and then we make the assumption that it has the same number of neutrons, and we kind of go from there. And the atomic weight, well, for hydrogen, is just the weight of the one neutron, because protons don't actually have mass. So that's the funny part about it there. So when you're gauging the size of an atom or anything, the nucleus determines the atom's weight, which only is this which only contains your protons and your neutrons. And so the neutrons is what actually gives an element its weight, and the proton number rarely changes. I don't think it ever really does, but the number of neutrons can change. And the symbol is just something that's agreed upon, because the symbol for hydrogen, it syncs up very well with the first letter being H, but there are plenty of elements in the periodic table whose symbol is letters that you don't necessarily find anywhere in the name of the element. And there's several reasons for that. And when we get to those, I'll definitely cover that. Here, this one gives a little bit extra information that you wouldn't normally find in these little cells, and that's the crystal structure. So not everything has a physical, not a physical, but a actual crystal structure. Sometimes they'll have to be assumed or basically speculated or theorized based on their properties and things like that. But hydrogen does have a solid form in certain conditions, and so they were able to observe the crystal structure of hydrogen atoms when they stack on each other. So they make a hexagonal form, basically. What would be a hexagon? What shape is a hexagon that you would normally see? Because we always know a stop sign is an octagon, but I don't think a hexagon too much.
No, listen, and I ain't gonna lie, stop sign popped in my head. I was like, no, no, no.
Me too. I was like, oh, I don't think that's it. Oh, a honeycomb.
Okay, okay.
And oh yeah, pull it back up. I think there was one more thing on there that was, oh yeah. So the electron configuration. This is super important, especially when she woke up on me. Especially when you get into upper level science, because this is going to determine where your valence electrons are, and also basically where all of the electrons are. So hydrogen only has one electron. So there's not a whole lot that you're going to see right there, but as you get to the larger elements, they're going to have, it's going to be a shortened or abbreviated version of that, and it's going to only be the valence electrons. They're really only going to show the valence electron configuration, because those are the ones that move around, that react, and all of that stuff. So other than that, the other ones aren't really important because they don't do much. And of course, they're going to tell you the whole name. So and then this, okay, so they have two different numbers here, the 1.00784 and the 1.00811. Though that's because all the weights are kind of estimated, because now we're getting to the reason why the atomic number only says the number of protons, because hydrogen exists as isotopes. So there's actually three different forms of hydrogen, and they all exist at the same time. And so the atomic weight is going to vary. So the 1.00784 is actually the if you were to, I guess, guesstimate how much hydrogen is in the atmosphere or whatever, and take the average of how many times you find any given isotope. So the most abundant isotope of hydrogen is the hydrogen with one neutron, one proton, and one electron. And that's the hydrogen we all know and love. That's oftentimes the reagent that makes water and all of that stuff. And it's called protium. That's the scientific term for regular old hydrogen. But then you end up with a heavier atom of hydrogen, because it has an extra neutron in the nucleus. And so that's going to increase the atomic weight by however much that extra neutron weighs. And that type of hydrogen is called deuterium, and is usually represented by a capital letter D. And then you have an even heavier form of hydrogen, which is extremely rare because it's not naturally formed in our immediate atmosphere. It's actually formed from cosmic rays hitting nitrogen atoms in our atmosphere and creating these free electrons and free neutrons that get picked up by hydrogen in the rain. So rain actually brings tritium, which is the third isotope of hydrogen, down to our atmosphere and onto our planet. And so that's why we now have tritium in our hydrogen pool of weights. And so the second number is actually the averaged atomic weight of hydrogen, or protium, deuterium, and tritium all together, based on the amount of abundance. So tritium is very, very rare, and it actually exists. You drink it in your water all the time. It's not toxic, or that's not going to do anything to you. It's just a different form of hydrogen. Well, not a different form, because it has all of the same properties for the most part. It pretty much reacts the same. So that's why you wouldn't notice that you're drinking it, or you're ingesting it, or you're surrounded by it in any type of way, because it doesn't really react in a different way than regular hydrogen. And it's super rare compared to the abundance of the one neutron hydrogen. And now we're getting to, bring up the picture with the protium, deuterium, and tritium, so they can see those differing. So this is what it looks like. So your hydrogen, your regular hydrogen or whatever, actually doesn't have any neutrons in its nucleus, which is why it's so light. So the weight of protium ion is just the weight of the proton. And then the deuterium is going to be the weight of the proton plus this extra neutron that came from uh, somewhere. And then probably a similar place as the tritium. Like I said, the cosmic rays hitting nitrogen and knocking off some stuff, and hydrogen coming and picking it up because it's very reactive. So it picks up all kinds of stuff, or stuff picks it up. And then your tritium is a proton and two neutrons. And there are a couple of different experiments that the scientists from back in the day did to actually classify the nucleus of all of these things to notice the difference between how many protons were present and how many neutrons were present. Because when they first saw this, they thought it was another element. Like at first, like that's how isotopes were found. Like it was a lot of stuff occurring, and they were like, well, where are all these other things coming from? And they realized it was the same element, and it was just kind of pieced together slightly different. And with this kind of speaks to the versatility of hydrogen, because not only can it do this with its elemental state, but it can also change, it can be either negative or positive. So you can have a negative hydrogen ion, meaning your hydrogen has an extra electron on it, making it negative, and they call that hydride. And that's why it can bond with the other elements in the group, because it can have a negative charge, and those the elements under it don't. They always will have a positive charge. They don't gain electrons. They only lose them. So that is why this one is colored differently, because it's a non-metal, and all the other things under it is what they call an alkali metal. And that's why those are always going to be positive, because the name alkali speaks to the oxidation state of those elements. So that I don't know, but for me that like kind of makes it crazy, because when you think about water, all of this stuff is occurring in water all at the same time. You end up with H plus ions, H negative ions if you add something that has extra electrons that it will lose. So like salts will do that very easily, and they tend to increase the electric potential of water for this very reason, because hydrogen is very happy with taking electrons or giving them. It's perfectly fine in either situation, and adding salt in the water increases the potential for it to accept or more electrons. And that's actually going to be seen in the experiment that we're going to do with hydrogen, so that's going to be fun. And moving on to the isotopes versus allotropes. Yes. So carbon is a little bit more fun to talk about, but as far as the allotropes go, because hydrogen doesn't actually have an allotropic form, so we have to talk about something that does. Carbon does. And carbon is actually also a non-metal, and that's why it's so versatile. Like, just looking at it, you have graphite sheets. I think those are used in several different industrial processes, and even probably like TVs and stuff like that. Especially in the tech field. So a lot of the stuff with carbon is used in the tech field. They have nanotubing. What else? The graphite sheets are actually used because they're great conductors. So the experiment that we're going to be doing uses a pencil because of the carbon or the graphite lead that is electron conducting. And I love how all this ties in. And diamond, as some people already know, is that coal is the starting source of diamond, which is essentially fossilized carbon. And then under great amount of pressure and heat, it turns into these pretty sparkly diamond crystals, but it's essentially just very, very hard and compressed carbon atoms stacked in a particular type of structure, which is this box here is showing the single crystalline unit of diamond. So it'll be that box, like multiplied a million times over to make one big sparkly diamond that we can actually see. And the fullerene, I forgot what that compound is actually used in, but it's a large carbon crystalline structure, and it's always found as C60. So it takes 60 carbon atoms to make this structure, and then that structure is, duplicated to make a larger structure that we actually see and use. On the other side, so allotropes, we'll get into the different properties of allotropes in a second, but I'm going to bring you to the isotopes. So the difference between the isotopes, as you can see, is the addition of a neutron. And that's what we just talked about with hydrogen having different names as you add an extra neutron. And carbon also can do the same thing. There are several different other elements. The non-elements are very easily linked to this type of thing. And I know maybe you might have heard of isotopes more so as radioactive things. So this is where that radioactive kind of aspect comes from, is the movement, the addition or the loss of these neutrons. So you can measure in elements what they call half-life, basically how long it takes for half of the amount of radioactivity to be gone from an element is half-life. And so that's how they measure that, and how much of how much of these things are gone after so much time. Oh, did you have a question? Oh, you can bring up the chart with the different elements of the allotropes versus isotopes. Yes. So allotropes are different forms of the same chemical element. So like how we had with, oh yeah, even with today's experiment, the tin has two allotropes. You can have a gray powder tin or a white powder, or the white form of tin, which is the sheet metal that is usually made. Oh, here, hold on, I gotta let her out. She just woke up, so she on the prowl for something to get into again. And then bring it back up. Yeah, there we go. Okay, and then isotopes are different forms of atomic structures of the same chemical element. So they are going to be the same thing. They're going to react very similar, as you can see halfway down. It says chemical properties are similar due to the presence of equal numbers of electrons. So like I said, electrons are usually ones that get busy and do all of the reacting and all of that. So having a different weight wouldn't really do much for you. Except for when you're using it as a reactant in something, and the molar mass of something is important. So if you don't have to know how much of an element or how much of a reagent you have is important, like the weight is, if that's not important, then it doesn't matter if you have the allotrope, the isotope or not. Because like I said, the reactivity is going to be very similar. And for the isotopes, some are stable and some are not, but allotropes are all going to be stable. So if an allotrope is unstable, you wouldn't find it naturally. Like you would have to create a certain type of circumstance or experiment or condition that would make an allotrope form and remain stable if you're looking for something that you don't just walk up on. So the nanotubing, like the neoprene and all this stuff, the different forms of carbon that we showed earlier, all of those were found like that. They were like, what's this? Like, what is carbon doing? And it's just like that. Like when you dig in the ground and you find diamonds, like we didn't create all of the heat and pressure of diamonds. It's in the front. It's in the front. Or here, you could take this one. Oh, she needs the charger for her phone. She didn't close the door back. Hold on. Okay. And for allotropes, the chemical properties are going to differ from each other because of the structure. So a diamond crystalline structure is a lot tighter than the what was that? The neoprene. That was neoprene. One of those. But then the other the C60 structure, as you can see, it looks like a big ball with hexagonal shapes of carbon all around. So there's a lot more space for a lot to go on inside of that structure as opposed to a diamond structure. So they're going to have very different chemical properties. They're going to react very differently, and they're going to have different structural capabilities as well. Like the sheets of carbon, that is actually a lot more flexible than you would think, but it's still very strong because it's still carbon. So it has a much different chemical property than diamond does. Diamond is extremely hard. Like only diamond can cut diamond. So that tells you how hard diamond is, and that tells you how it's not very reactive because of its very hard and tight structure. And is not found in all chemical elements. So you will not find allotropes in every type of element, but every element does have isotopes, every single element, so everything. And taking all of this into consideration, you have to understand we are organic creatures. We are made up of all of the stuff that's in the periodic table for the most part. So you have all of these different forms of each of those elements in your body for however long. Even if it's just a millisecond, it's still going to shift back and forth between those forms, given different uh like reactions and things that's going on. So it's very interesting how when you understand that everything in your body is constantly in flux. It's constantly changing. It's never at a resting state. Even when you're sleeping, your body is probably a lot more active than you would think, especially since you're not controlling it with your mind. You know, your conscious mind. Your body is like, okay, good. Now I can really take the wheel, and trust me, it's joyriding. All right, it's going. It took you for a whole joyride while you're in La La Land dreaming. It's having the time of its life. But moving to the a couple more facts. Did I say it? Oh, so one of the real world examples I wanted to kind of bring up is hydrogen cells. Hydrogen cells are very clean and very what is that, abundant energy source. So Tesla, the Tesla cars, they have hydrogen fuel cells in them, and you can just recharge them with electricity because that's what keeps the electric potential in the plates for the conversion of hydrogen to basically water vapor because it comes out as a gas. Otherwise, you see little water trails behind all the electric cars because they be leaking H2O, but they don't. So it's actually comes out as water vapor, as H2O gas. So that is why electric cars are much safer for the environment because they don't have CO2 emissions, which through many, many years of environmental science, we now understand are what they call greenhouse gases. And greenhouse gases basically create like a reflective barrier for those cosmic rays that I told you about that creates deuterium and also traps the UV rays, but not just the rays, it's also the heat. So the heat is actually the biggest problem with the CO2 gases. It's not necessarily that it's bad because we breathe out CO2. So it's obviously not toxic in that way, but it's toxic in the way of increasing the Earth's surface temperature, which doesn't seem like a lot. Like global warming is based on like point oh something 1 degrees Celsius like above what it's supposed to be, and ice caps were melting. This was years ago. Like now it's like bad. Like it's very bad. Like we're in the middle of basically a global warming crisis at this point because this was when I was in high school. So for about like the past like 15 or 20 years, like policymakers have been, at a war of something that they don't even understand. Like none of the policymakers were scientists from what I've seen that were against global warming. None of them were actual scientists. So they didn't really understand what they were even talking against. And if you look at a lot of the way that the policy making was going, it had a lot more to do with money than it did with actual like environmental or scientific rebuttals to, you know, them saying we're we're ruining our planet. We got to put more money and effort into researching renewable energy. But it's like now we're kind of, you know, playing catch up. So private companies, not the government, unfortunately, fortunately or unfortunately, I don't know how how I want that to go. Like, unfortunately, because you would think that they would have our best interest in mind, and you know, with the policies and the budgeting and stuff. But then, like, fortunately, because it's like whenever they have their hand and stuff, it gets kind of, you know, janky. So I'm kind of glad that private companies are funding more research into renewable energy, clean renewable energy sources, and hydrogen fuel cells are one of them. And another way to actually I would say give the electric potential to a hydrogen fuel cell without having to use more energy. Because, you know, when you think of electricity, it's energy involved. So you're either burning coal, using hydroelectric power, a battery, or something like that, but it still requires some other type of energy source. You have solar panels now. So the fuel cell for solar panels is a hydrogen fuel cell. So houses that are fitted with solar panels, they have a hydrogen fuel cell probably hooked up somewhere in their basement or utility closet, and the panels convert the UV rays to energy and is stored as electric potential in these fuel cells. And then when the sun goes down, you can now switch on your generator and it's going to draw the energy out of that fuel cell. But here's the good part about that is that if you are a homeowner and you get solar panels put on your home usually within the month, especially if you're in a very like sunny area, like a lot of the western states probably have really already done a lot of this, but you can end up providing electricity to your neighborhood, and the energy companies will pay you. They will send you a check for the amount of electricity that you have brought into the grid and serve, because the electrical grid just pulls electricity from wherever there's an abundance. So if you're providing more than what you need, you could potentially tap that energy back into the grid and make money. So that's why I think that was probably like one of the few policies that our government did do. They added like tax breaks and tax credits for people who who set up their homes with these type of fuel cells, the solar panel with the hydrogen fuel cell. And you know, then the electric companies, by way of, you know, doing business, they have to pay you for it. So you're getting like a double, you know, a double dip on, you know, just trying to be helpful to the environment. And you know what's rewarded, right? Ain't that what God said? All right. So, you know, you take care of the planet, it's definitely going to take care of you. And with hydrogen being one of its well, not one of it, but its absolute most abundant element, like, you know, that's definitely the first place to look for energy. But then, you know, that's a double-edged sword, as we have seen with the atom bomb that was created from Albert Einstein's research. So his theory of relativity was kind of perversed into this devastating bomb that was dropped on Japan during a very unnecessary war for both sides, honestly. And it was a very big step in science and a very large backward leap for humanity in my eyes. And we have learned a lot from that you know, that tragedy, because it's a tragedy. I don't care who we were at war with or whatever. It, like, that was terrible. It was women, children, families, schools, all that stuff that was destroyed. And that shows how unstable hydrogen can be, and all they did was just kind of control where it becomes unstable, and that was the result of it. It literally obliterated an entire like city, almost, like pretty much like a very large, and they dropped two of them. So you can imagine like just how much effort was wasted, because like that much energy we could have been, you know, giving free electricity to, you know, schools and hospitals and things like that. Like what Akon is doing, he's you know, using his fame and his influence to get clean energy into very obscure places in Africa. So, people aren't, having to struggle and things like that. So there are much better way to use this type of knowledge, to use this type of access than to kill each other. And I'm so glad that a lot more people are starting to invest in that, especially the large corporations with the influence and the money and the resources, and they're coming out with some pretty amazing ideas, especially in how to keep people safe when using these things, because like I said, hydrogen is very unstable. So uh, it's uh, it's not used in its pure form, but it's basically, if the cell is in open air, like I said, hydrogen is most abundant, so it's going to be in the air. But the thing about not using pure hydrogen is that you end up with byproducts of other stuff that's in the air. So they, they figured it out. Like I'm still just on the overview of everything, but they have definitely figured it out, and they're looking into a lot of other things, because like I said, it's a global crisis at this point, because water levels are rising, and there are whole cities that are like essentially drowning. Like I think somewhere in France there used to be, like, the nice little, the Blue Danube, the song, the that I think was Beethoven or somebody had composed, was about, the little river that runs through the middle of France. They like to have the paintings with the guy on the little raft pushing, like, oh, you enjoying your vacation or not? Like, I don't think that's a French accent, but that water level is high now. So anytime it rains, it's always a fear of flooding. It's always a possibility of flooding. So they tried some of everything, and at this point they've created a hydraulic lift to lift the entire city up as the water level rises. So it's almost like creating a city raft. It's strange. So like it's a lot of places like that, coastal places, that are starting to experience that a lot more. So now it's not a question of if it's global warming. They know it is global warming, but now they have to come up with solutions as opposed to prevention. And prevention, we know, is the best medicine. So it would have been better if you just didn't ruin our environment. Oh, so, but we're here now. We're already in that boat in high water. So whatevs. But that's like a lot of awesomeness all wrapped up in one little tiny element. And like I said, it's the simplest atom, the simplest element. And it doesn't even have a neutron. Like it's literally just a proton hanging out with it. That's why it can do both. It can do the because the neutron actually is what kind of anchors the proton. So it makes the proton a little less, reactive. But elemental hydrogen with one proton and its little happy electron is very, very versatile. And I kind of want to embody the spirit of hydrogen and how it moves, because it's involved in everything. And when you think of how just changing one hydrogen on a molecule or on a compound changes this whole chemical reactivity is crazy. And as I mentioned in one of the earlier shows, like even just doing the math of the energy, the thermodynamics, and the physical, excuse me, chemical properties of hydrogen is extremely complicated, and it's the simplest element in our solar system. So it's amazing to think that something so simple is so complex. It's like, how can you not see yourself as being so complex, and we try to make ourselves so simple, and that's like impossible. Like, why would you even bother to try doing that? Like, be like the hydrogen, be complex, be look simple, but be complex. Those are two very different things. And I love it. I love sitting in that space and just looking at how everything like really just comes together. Where's my pencils? I gotta make sure. So now we're getting to the fun portion. Are there any questions before I move us on?
No, but I have a comment. So it was interesting when you said like all the things that's going on in water. And the first thing that popped in my head, but it's so plain tasting. It's, it's so plain tasting. But when you explain everything, I'm like, You would never think that all that was going on in water.
Uh-huh. And actually, for me, water, I can taste the difference in different waters. Like you can take probably take water from like different faucets in my house or something, and it'll probably taste, and I could taste the difference. Like because we have a filter on our kitchen sink, so I don't drink like sink water. I wasn't saying that I don't drink sink water, but at one point I did drink unfiltered sink water, and mine tasted different from somebody else's, and filtered water tastes different from bottled water, and all of that stuff. And it just depends on how your body is set up, what your taste buds are like, and all of that stuff. Because not everybody has a I guess you could call it a sensitive sense of taste. Like some people just like it tastes like nothing. Like, but like when you really put your mind there, like, no, but what does it taste like? And given where you stay, the state that you live in, different environmental regulations, different things that's occurring near you, your water is going to taste different because all of that stuff is in your water. So if you live near any industrial complexes or factories, facilities, anything that manufactures anything, your water is going to taste different from someone who lives on the other side of town, like in a completely residential neighborhood with none of that near it. So it's important to think about that when you're planning, relocation or wherever you live. Like, well, what is it by? Like, not just looking at the school district, because it might be an amazing school district, but then your water supply is crappy. And I actually came across that kind of stuff when I was doing the research for the new hormone balancing program I'm doing. And when it said that, like, you are exposed to so many contaminants in your environment, just in general, like not even on purpose or none of that. Like in all of the pesticides that are used on like everything, 90 something percent of those don't have to be, because of the way regulations and stuff are, 90% of those aren't tested for human effect. So they don't know how they're going to affect humans, how it, whatever. So a lot of like birth defects and stuff like that are, could very well be linked to any one of those pesticides. And even testing the cord blood of an infant. This is someone, a newborn, someone who has never, like, just barely taken their first breath of air, could easily be contaminated with over 200 contaminants. And this is just from a woman living her regular life. And she could, and even if, like, you're, doing everything, you eating healthy and all that, the vegetables that you eat, contaminated soil from pesticides. Even if they say it's organic, I'd be like, okay, that's fine, but you can't control where rain clouds come from. Last time I checked. So that's why I'm not one of the, I don't really, spend the extra money on organic stuff. I just want it to be fresh vegetables, because the benefits of eating the fresh vegetables actually far outweigh the I would say the negative effects of whatever could be in it, because that's just how nutrition works. So that and especially because we don't actually eat within our food chain like animals do. Like animals can easily end up I don't know. It's called biomagnification. So if you have plants in contaminated soil, let's say mercury, mercury is in the plant now. So whatever eats that plant is now going to have mercury in it. So because our diet is from all levels, we don't run into back biomagnification as much unless you eat a ton of meat. And then if you're eating not primary consumers, so primary consumers are the ones that eat the plants. So we can be a primary consumer and eat plants, but we don't digest it as well as natural primary consumers like that are primary consumers. We're more so considered omnivores because we can get our nutrition from meat and things like that. But herbivores or primary consumers never eat meat. They don't eat anything but plants. And then if something eats that animal that has eaten the contaminated thing, it actually has a higher concentration of mercury in the animal than in the plant from the soil. And then you eat that animal. So if you're eating a full on carnivore, you could very well, but this is like if you're in the wild. So like all of our meat sources now come from farming. That's why we even started farming, because you can control a lot more. So if you know that the soil that you're feeding your animals from, or like the feed that you're getting your stuff from, um okay. The feed that you're getting the stuff from isn't contaminated, then obviously you don't have this problem. So that is why we started farming, because biomagnification was a big problem, and it was noticed a lot quicker in fish, and that's why a lot of they were. I don't know if anyone experienced the fish warnings, but that's why there were so many levels of mercury in fish warnings, because biomagnification happens much quicker in the ocean world than it does in like the plant to animal world, because oh, it's not in here. Oh, here, because the fish eat other fish all the time. Fish eat plankton, fish eat, and then they're in the contamination. So the contaminant is actually in their living environment. So they're being directly contaminated and also eating things that are contaminated. So the biomagnification tends to happen much quicker in fish, which is also why we started farming fish. And so yeah, so
Okay, so real quick, so farming fish is pretty much a better option than the natural way, so to speak.
I mean, not necessarily, but it's not worse. Like a lot of people are, I guess, more put off by like the genetic modifications than anything. But most of the genetic modifications are either for speed of growth. So like after they give birth, they grow bigger quicker, like sooner. So as opposed to it taking 9 months to mature, now it takes 3 or 4.
Well,
So it's not like a large genetic change.
I'm glad you said that because it's so funny. So I eat tilapia, right? Fish. And people be like, don't eat that. It's whatever. It's farm raised. It's not even pretty much like it's fake and it's harmful. I'm like, well, I don't know. That's what grace is for. I'm gonna say grace over anything I eat. And
And that's pretty much it. That's all
but
you can
it's
do. Because
funny that you
no, go ahead.
explain that. So it's not bad. Because that's what they were making it seem like it was bad. Like
Oh yeah, no, it's not any work. Here she come. It's you see how she just slammed the door. Like, why is this door closed? It's not any worse for you than, I guess, anything else that's bad for you. Like the same people that kind of have those type of hangups and all of that eat McDonald's, and I call McDonald's burgers mystery meat. So if you eat McDonald's, like you can't tell me about GMOs and all of that stuff, because it's the same. It's the same in the same lane of give it some time, it'll kill you. Like, but for the most part, like a lot of like, oh, careful, girl. She's standing on the ball behind me. A lot of the genetic modifications are basically to make it so that we have food to eat, because we've ruined our environment. The pesticides have created superbugs. So not just antibiotics doing that, but the pesticides make it where these bugs survive everything. So they eat the food before we even get a chance to see it. And then, now farmers are losing money. So that's really where the USDA had came in. I think it was it Roosevelt? I think it was Roosevelt. He had the SNAP program that we now use with EBT and stuff like that. That actually stemmed from the government subsidizing farmers, because they, their people weren't buying their food, like the crops weren't doing well. Like it was a lot of stuff, because I think it was like the depression. So they had the Dust Bowl. Like it was like right behind like a whole lot of stuff. There were droughts. So he subsidized the farmers and all of that stuff until they got on their feet, and then the program just never really went away. It kind of just transformed into something else. But all of that stems from the stuff that we were unknowingly doing to the environment. And then even once we knew what we were doing, we kept doing it, because it was just easier than finding a better way that was less stressful on the environment, on produce, on plants, on our bodies. So we're really starting to kind of see the effects of what they were doing with the world 60, 70 years ago. So our grandparents may not have really experienced those effects, but we're definitely seeing it now with all of the chronic illnesses. Most of those are due to different forms of inflammation, and inflammation comes from contaminants. So our environment is riddled with contaminants. Like we're really just now getting lead paint and copper pipes out of the out the way. So we're still catching up to everything that's contaminating and killing us. But it is experiment time. Okay. Hold on, let me close the door again because she didn't bust the door open. Got J. Cole bumping in the background. All right, so I'm gonna change the camera angle. Let me put my goggles on. Safety first. Yes, so we'll be doing our hydrogen experiment now. And it's super simple. Um, Especially if you have any of the leads. So the leads, you can probably get those at like any like hardware store, or you can just use insulated wire. It doesn't have to have clips or clamps. And the pencils, all I did for the pen, you can see what I'm doing. Yeah, all I did for the pencils, these are, as you can see, like two little regular pencils I had, and then I just pulled the eraser part off. Like they're super cheap, so the cheaper the pencil, the better, because it's going to be easier to get this thing off because they don't have it on their mill. So I just took the eraser off of one end, well, off the eraser end, and I just sharpened both sides of it. So you got lead. Let me see, can you see that? Yeah, so you have the lead on both ends of that, and you want that exposed. And then this water here is regular water, regular sink water, and the beaker is from the Mel Science kit. So they send supplies. The tray is too. They sent gloves with the experiment too. So this is from the 10 hedgehog we'll be doing, and a piece of cardboard. I cut this off of a box that I had. So yeah, and then I just stabbed 2 holes in it. The pencils will be going through that. Then this also came in the Mel Science kit because there's another 10 experiment where you can make 10 dendrites, but you would need an electrical potential to produce the redox reaction that generates the dendrites. And regular batteries, and they have the little leads on the end. So first we'll put the pencils in the water. And then you want the pencil all the way in the water, but you don't want it to touch the bottom because the glass will end up grounding it and you won't have an electrical potential anymore. Which is why, so I'm watching Black Lightning last night. Black Lightning is my show. Okay. And I'm kind of sad that they not coming back for another season because it was good. And I heard they had a couple ideas for some spinoffs that I definitely would have watched. But he ended up getting buried alive. And so he was, yeah. Oh, it get real jazzy. So he's thinking in his head, like, oh my gosh, like I'm grounded. Like he's electrical, so he has electric powers. So if he's in the ground, he's literally grounded. So the dirt, the earth, that's why they call it grounding. The dirt and the earth pulls the electricity down to it because of the magnetism of the earth's core. So the electricity seeks the earth's core, and that's why the ground grounds electricity. That's why lightning even strikes towards the earth. If we didn't have a magnetic core, lightning could strike in random directions or whatever, but it doesn't because of the magnetism of the earth's core. So he couldn't do nothing. He ain't had no power. But there's a twist. So the explosion from the Markovian invasion or whatever created this little, radioactive power source in the bedrock under where is they called? I forget where they live, but the town that they live in. So he was able to pull the power out of the radioactive rock and get up out that jam real quick. But that's why it's that's why it's fiction. But it still had a very good handle on the science of electricity. And so our electric potential that's going to be caused by this battery. So the battery creates the electric potential. The water is going to I almost forgot my salt. So water itself doesn't conduct electricity as well as people think it does. Another some more movie stuff. It does conduct electricity, just not like, oh, it's like amazing. Not when you're trying to do stuff like this. So salt helps that process along. So we're gonna put a little bit of salt in the water. It's just a couple of flakes. We're gonna swirl a little bit, let some of that dissolve up in there. And the salt ions, what they do is they just add a little bit more action potential to the water because of the salt ions roaming around in the water. So it just encourages the electric transfer a little bit more, and then you'll see the bubbles faster. So I want to try and make it where you can see the stuff a little bit quicker. All right. Then pull this clip back, and then now it doesn't matter which one you clip it to as far as the pencils go, but you want to make sure that the end of this, that the metal part is attached to the graphite lead end of the pencil. And then the important connection for these clips is to the battery. So you want to make sure that the black lead is attached to the black wire on your battery. Okay, there we go. So black to black and red to red. Don't cross anything or you could explode something. Kidding, not kidding. And because it's a battery, there's no switch to flip or nothing. Once I connect this, it's going to go ahead and start doing its thing. And then that's just going to take however long it needs to build up the potential. And then I'll try and hold it up so y'all can see that closer. But this is the setup, and we're just going to let that do its thing for a little bit. And because of the, I don't know if you can see this. Here, let me pull it in closer. So the bubbles are actually starting to form pretty quickly because, like I said, I added the salt. So for this one, okay, the black is usually the anode, which is can you see the bubbles forming on there?
Not really.
Here, let me try and get it closer. Here, put the light down. Okay, can you see it now?
No, sorry.
Let's see. Is that close enough? Let's see. Oh, that's my mic. My mic was in the way. Here, maybe without the white tray you can see it. Can you see it with the black surface better?
Okay, at the bottom. Okay.
Yeah. So the bubbles around the bottom of this blue one is connected to the negative or the anode on the battery. So because this negative electric potential is going through this one, it's attracting hydrogen ions to it. So the electrical potential at the end of this pencil is electrolyzing the water and separating it into hydrogen atoms, or that gas. The little bubbles are actually hydrogen gas. And then on the other one, you're getting oxygen gas. So it's turning the water into hydrogen and oxygen gases.
That's neat.
Yeah, I feel like MacGyver. Love that show. I think, like I said, I think that had a lot to do with me going into like the sciences and stuff, because I was just like, he just knows all kinds of weird randomness, and it was like whatever situation he was in, he was gonna figure it out, and he did something kind of like this, but I think he made like a bomb situation, but that is electrolysis. So this is how they do basically electroplating. So you can potentially put, instead of having the other end be the pencil lead, you could even have like a metal clip and clip like a key or a ring or excuse me, or a chain to it. And then instead of just having salt in the water, you could have like this, a tin chloride or whatever type of metal you want to plate on there. You would have a solution of that metal in the water basically, and then when you turn on your electric potential, it'll draw the positive metal ions to the anode or the black end. So you would have your chain, your necklace, your ring attached to this, and then you would plate it with the metal ions out of the water. So that's how they do gold plating and all that stuff. Like that's how they do all of that, just like this. And you could even, like I said, you can gold plate and stuff at home. Like it's people on selling stuff on Etsy right now that they didn't plate it at home, and it's just that simple.
Girl, I was just ready to say I'm about to start making my own costume jewelry.
Yeah, you can. You absolutely can. You can use metals that you're not allergic to, so you don't have to be like, is that copper or is that silver? Or you don't have to ask because you already know because you made it.
Right. Listen, hair store won't keep getting my dollar.
Okay. So here we'll get. Do we have a? Oh, it's in the box. I think this sits in something. Yeah, here we go. Okay, this is for our tin hedgehog. And this one is very simple. They already have, because I saw a video on like how to make tin 2 chloride solution, but you would have to have access to chlorine. And I believe chlorine is a controlled substance because it's very poisonous. It's highly poisonous. And so yeah.
So real quick, so the levels that are in, like, public swimming pools and stuff, there's chlorine in there. So
Oh yeah, that's not elemental chlorine.
okay,
It's
okay,
yeah,
okay,
yeah,
okay.
and that's the thing. Once something like something could be have different properties and capabilities, and it's either its elemental or atomic form. But then once you combine it with something else, it makes it safe. Just like magnesium is extremely reactive, lithium highly reactive. It explodes in water, but in the salt form, lithium hydride, you can ingest it. That's usually the form that it naturally occurs in, like foods and things like animal, meat and stuff like that. That's how your body gets it. And then it does what it needs to do with its reactions to, absorb it or use it somewhere else. I'm going to get some cigarettes. Okay. And so just that's basically what science and developing different things, that's ultimately what those experiments are. Like, how can we make this safe for people? And so that's basically all they do with the pool chlorine. Is it's not just straight chlorine. It's usually in a different form.
So I was thinking. So when you said magnesium, am I right? Isn't that like a form of like a supplement? Can't you take magnesium
Oh
or
yeah, for
no?
sure. Yeah.
Because I
Broccoli is
remember.
very high in magnesium though, but most people I guess don't like broccoli.
But that's one of my favorite vegetables. That is one of my favorite because
Mine
I'm
too.
like, wait, it's dangerous. But then when you explain, like when you combine it with certain things, it takes the harm away from it. Because even with the coronavirus, I remember magnesium being one of the supplements I kept hearing about. That will give you a healthy immune system.
Let me make sure I got the right bottles. Oh, okay, this is the dry one. I need the liquid one. Here we go. Okay, so they because like I said, there's two different experiments. One has the dry form, but I need the liquid. Are any of these in the liquid form? Oh, they could have told me, so I got to make my own. Yeah. So now this is where we go. So we just add our acid to this. So the acid is going to activate our tin 2 chloride. I'm gonna put the whole bottle in. Let me get the top. And then they give you a separate color top because once you mix that in there, there's no real way for you to know that that's not just 10 chloride. So they give you a different color top to once you mix the acid with the 10 chloride, you don't, you know, confuse it. Like, no, this isn't just that anymore. And so even this, the sodium hydrogen sulfate, so the sodium hydrogen sulfate basically makes that not sulfuric acid. Sulfuric acid is a very corrosive acid. Like I said, I set a paper towel on fire with it before, so it's yeah. But the sodium kind of dials down its little situation. Okay. And so then I'm going to add this bottle to my 10-2 chloride. Did I grab my, I was like, did I grab my instructions? So here we go. And then whole bottle goes in. How was they going to expect me to take this little stuff out? They got the bottle all stopped up and they want me to pour it. Girl. I guess I'm supposed to use the lid that's open. So this one doesn't have nothing in it. I'm like, they got this one all stopped up and they want me to use that. Make it make sense real quick. All right. And so we squirt that in. We want to be careful that we don't splash it. And put the whole bottle. And I think this is also how they keep the experiment safe to do as well, because they've already pre-measured everything and all of that. So if you do have to mix anything, it's not like, oh, I got to measure this into something else. And nah, 1-to-1. Okay, shake it. Shake, shake, shake. Shake, shake, shake. So I'm going to dump that out. Then now it says fill. So I'm going to put this, I'm going to just reuse the top. I'm going to put the old stop back on there in the cap. That's not the cap for it. Yeah, in the cap. And we're going to put that back. And this little thing, this is actually, I believe this is what you use to dispose of the stuff when you're done with it, because it's toxic for the environment and the water. So you want to make sure you're disposing of your post-experimental reagents and things properly, because you could very well contaminate the environment. So when I worked in a lab and when I was at school, we had a whole separate container that we dumped all of our old experiment solutions and stuff in. And then a chemical company came and would pick it up and dispose of it. So obviously we won't be using chemicals on that level to where we will have a whole big dump container. So they have a way that you can dispose of it. And you can call your local I guess it's like the chemical and poison center people, and they'll tell you how to safely dispose of whatever stuff you're using for your experiments. Even if even if they do, because sometimes they have like a drop spot where you can take the stuff to, like clinics and stuff like that. So you might be able to find something like that. But proper disposal of all reagents are a must. So now we're going to fill this up halfway. Ooh, making a mess. That's why they have gloves. And then we fill this halfway up. Oh, that's not half. Get back down. Okay. Close enough. Works for me. Good enough for government work, as my mom would say. And then we're going to take this and drop it in there. And so this is going to start reacting and forming little tendons on it. Oh, it's actually doing it pretty quickly. Oh my. Can you see that? Let me get close. Here, I got to bring y'all in the light. Step into the light, my child. Let me take this contaminated glove off. All right. So let me double check if y'all can see, not with the ungloved hand. So let me see. Can you see that? You see the little sparkles on there?
Yeah, I know that. Yeah, you can see that.
Yeah. This actually started happening a little bit quicker than what I thought it would, because they said like 15 minutes. But I guess like the big, like fluffy looking one, that's how it'll look after about 15 minutes. But you can start seeing it forming on there like almost immediately. And it's just sparkling away.
That's neat. And like you said, that was quick.
Yeah. And you can see it's starting to get real sparkly now. And oh, you can't see that this close, but I can see it. You can actually see little like, have you put like sugar or salt in water and you see it dissolve?
Uh huh.
That's
Uh
that's
huh.
what it, yep, that's exactly what this looks like. You can see the zinc. So the reason why you can see the tin on there is because the tin is actually replacing some of the zinc on that little pellet that I put in there, and there's actually zinc 2 chloride being released back into the solution, and the density is going to be slightly different because zinc is heavier than tin. And so that's why you can see those little swirls of the salt or the sugar dissolving, because the sugar molecules with the water is denser than just regular water. This was nifty. That was nifty and fun. I do have one more that actually came in the box. That's what the other that's actually what those electrodes are for. The little things that I use for the hydrogen experiment. So that's what this is for. So we're actually going to go ahead and do that one because we already have the stuff set up. So may as well. All right. So let me get the petri dish. Okay. Move this out the way. And I'm still going to let the little hedgehog grow while we're doing this one. So by the time we finish with this one, the little hedgehog should be a little bit fluffier. Let's be careful not to break the gloves or rip them. And I can smell that the sodium acid on here. Like sulfuric acid, it smells like burning hair. Making it smells like, oh, hold on. Because my mom then went to the store. I gotta let her in. Come on, get up. Come on, bug. Hey, hey, hey. So sulfuric acid absolutely smells like sulfur. Like, smell is one of the chemical properties of things, but sulfur is one smell that never changes. Okay, so I actually made, yeah, I got enough. This is a half a bottle. So I actually have enough, I think, because we put the whole bottle in there. It says 1 bottle. So we should be able to do it with half. So we're going to put this in there. So the first step was basically making this like we already did. And then we pour this on the thing. Yeah, that might not be enough. We'll see when we add the soap. And so, getting away from me. So basically the reason why we have this liquid soap is because as you can see here, the solution doesn't have enough, surface tension to cover the whole petri dish. So we're going to drop some drops of the soap, which is going to help. Good grief. They got all this stuff capped off, which is going to reduce the surface tension of the solution that we made and allow it to spread better. Where's my dropper? And she just acrobating standing on the ball. What, does this one not fit on there? I guess that one doesn't fit. So we're just going to carefully drop it then, since there's no dropper that'll fit. Okay. Do. And so, I don't know if you saw it, but as soon as I added the soap, it immediately went on ahead and spread on out. So, there are a lot of processes, industrial processes and stuff that uses liquid soaps for that very reason. because it's not like just cleaning. What soap really does is it encases individual like atoms and things and molecules and separates them to keep them from binding together, from having any type of electrical or attraction or anything, and that's what makes surface tension of water. Because hydrogen, like I said, it bonds very easily to a lot of stuff, including itself. So that's what the surface tension of water basically is. And then where are we? Oh, my cathodes. So now we clip these on the edge of the petri dish, and we got to make sure it is touching the liquid. And we're going to set it where it's on opposite sides. Make sure it's in the liquid. And then we got our battery over here. We connect it. And then this is going to make the tin form metal, like little metal arms across the top of this. So let's see if we can get that going. Okay. It's in there. Yep, right polarity. Okay. And then let's see, it's got more. So the electrons from the batteries cause a chemical reaction, one of the products of which is metallic tin. Oh, it's doing it. It's doing it. It's doing it. Let me try and get it where you can see that. Okay. If you look on the black side, you can kind of see them starting to reach out. Can you see that?
No, cause I don't know. Okay.
Let me pull this light down. Maybe that. Okay. Yeah, that helps a little bit because it's reflecting the light. So it's starting to reach out further now. Can you see that? Oops. Let me not close it because my laptop will turn off on y'all. Can you see that?
Okay, so what am I looking? Oh,
On the
okay.
side near where the black side is, you should be able to see it looks almost like ice starting to form. Like little
Oh,
leaf veins almost, but it's metallic silver. Like it's a silver color.
that's crazy that you did that sitting there.
I know, right?
That is neat.
And the crazy thing is that when you look at the pattern, that's what the blood capillaries in our body look like. So when you think of how your body is all basically electrical potential, every signal that's sent from your brain to anything in your body is electrical potential, and you have all of these different things in your body, like the actual physical form that transports that stuff around looks just like this. So it's like there's natural patterns that everything follows. And that's what Fibonacci he did. He found patterns with math. So the Fibonacci sequence is seen in everything. So flowers, seashells. What else did they show? Like it was pretty much everything that had a pattern followed the Fibonacci sequence in some kind of way. And even like looking at how this is branching, it's still kind of following a sequence. So the first initial branches were only like two or three, and then off of the initial branches you had like two or three, and then you had another and it was like six or nine, and it's starting to like branch more and more towards the red side. And it's silent. It's happening in silence. Like that's crazy. Let me try to get you in close.
Yeah, that is so cool.
It looks a lot crazier like up close and in person. Duda. Buddha bug. I hope she don't end up closing the screen on y'all. Duda.
Hello. You coming to do science Just
So we are well on our way on our journey through the periodic table. I promise I won't take y'all through all 100 something of the elements. Because for the most part, I'll end up covering the groups together. So next week we'll be covering. Girl, stop the rest of the alkali metals. So hydrogen, like I said, is a non-metal, which is why it's colored differently, but it's still coupled with those because it reacts kind of like those do. So the groups describe reactivity, and everything in the same group reacts similarly, except it has more, it has more mass, more electrons, and more stuff that goes on, but it will react in a very similar way and can easily be interchanged with anything in the same group, as it yeah, as you move down or up the group. And that's going to be fun. So like I said, there are I believe it's that, yes, it's that one. So there'll be some videos that I'll be sending for next week, so we can watch it in action, and then we'll cover those and kind of how they play into our life. And like I said, those are trace elements or trace minerals that our bodies do need, and I'll cover that too. Right. Say hey. Say hi. She trying to figure out who she said hi
her face is like,
to.
what?
But it was so much fun, and
It really
thank y'all for
was.
tuning in. And I hope all of this was as fun and amazing to y'all as it was to me. And this is like going crazy right now.
Listen, like I said, I'll be learning. I get off here with some more knowledge than I came on here with.
Hey, that's always the goal.
God. Wow.
And oh yeah, I already did receive the next experiment from Mel Science. And here, let me unbox it. Oh yeah, certainly. And like even our regular sources of entertainment are finally starting to catch up with, everybody's thirst for knowledge. Like Netflix has a ton of specials and things, and documentaries and stuff that they, I guess, have personally funded because they got their little red N on them. They make sure, hey, we gave the money for this one, so give us the credit. But they do have a nice little selection of like body type documentaries that tell you about the science of the body. What's it called? Human worlds, I think, something like that. And then they also have like developmental ones. Like I watched the one with the babies. That one was great, especially because she was like real fresh when I watched that, but it was super useful for like a lot of stuff. And it even talks about like child development through pregnancy too. So it was very, very informative. I learned a lot of stuff. They talk about the brain, the mind, all of that stuff, growth, development, different milestones, even things that you wouldn't know or think. Like I would say the most mind blowing fact that I learned was that, how people kind of, say that mothers have like a tighter bond with their babies or whatever than the dad. That's actually not true. And well, it doesn't have to be true. So basically, if the non maternal parent, so obviously if you didn't give birth to this baby, you're not biologically going to make a bunch of oxytocin. So if you care for the baby as often or as much as the mother does, and hold the baby and all that stuff, you as a man, y'all men out there, can produce just as much oxytocin as the mother. So you can bond, and that's what the bonding is. So if you bond appropriately with your children, you can have just as chemical biologically chemical of a connection with your children as the mothers do. So you don't have to be like, oh well, because she the mom and she the birth and she breastfeeding and that's fine. And all that stuff does play into all of the hormones and stuff that we experience as mothers, but it's not exclusive to us. So just be we just have Father's Day. Just be good fathers, bond and spend quality time with your children, and you can share those same feelings, those same emotional roller coasters and heart attacks that the mama have. And like that sense that moms get, like, I know something wrong with my baby. Like dads can have that too if you're bonding and you're spending the appropriate time to bond with your children. So don't let nobody tell you that you're not as good of a parent as the mom.
When I mean, but and so when you think about, when you put it like, it does make sense. That's like your best friend, be y'all, when something's wrong with that person or anybody that you've created with a bond with. And how do you create a bond with somebody? Like you said, you interact with them and you begin to know a person, even if they like, oh, nothing's wrong, you like, yes it is. Or like you said, you can just sense it. So yeah, that it do make sense. That makes sense.
So this is the next experiment. It's called fire foam, and the metal in this one is iron. And I'm gonna have a whole mouthful to say about iron, because iron is all up in your body, known as blood. So the main complex of your blood cell makeup is the heme molecule, which is basically the physical structure of the proteins that make up your blood cell. And in the center is an iron atom, and it has all of these nifty little connections. So I can't wait to show y'all the structure and how our blood does its thing a lang with the iron. Okay, and that's why anemia is so can be so life threatening, because your blood is made of from iron. Like all of its function relies on it binding iron. So this is going to be a nice next month. So we'll be going through our alkali metals and iron.
That looks so super neat.
Oh yeah, I can't wait for this one, because I think I've seen this before, and it almost looks like if you were able to set steel wool on fire, but not with flames. Like it almost looks like a ball of burning hair. Yeah, that's probably more accurate. But yeah. So that is the show for today. We went over a lot today. Yeah, I wasn't even intending to go this long. I don't know. I went off on that global warming tangent, but I had to make sure that the info is out there, because the next generation is who's gonna save us. They're gonna end up finding a way. We're gonna have floating cities and cities in the sky and all of that, because some fifth grader solved, I don't know, some unsolvable scientific equation or something, because they coming. Okay, I can't wait. As soon as this one start talking, I don't know what she gonna build. So definitely invest in your kids, pour into them, because they have all of the mental elasticity needed to absorb all this good info and do more with it than we thought we could. You ready to go, Bud? I gotta get get her situation together and feed her.
Well, listen, thank you for taking us to school one more again, because it was.
Oh yeah. Oh, you see my goggles. We got it. There we go. Woo! Scientists in the making. She likes them too. She trying to hold her head steady so they don't fall out. She don't know what's going on. I was checking my dendrites. Oh yeah, before we go. So this is the little hedgehog. Let me see. Can I see that better? Yeah.
Oh, yeah, 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 yeah. I can see that. I can see that. That is so cool. Like something that's literally growing.
Mm-hmm. And all of those little symbols on there is 10.
Look, my child in the background singing. I'm sorry.
Yep, all with a little bit of chemicals. But it looks so pretty. But it's gonna, yeah. So I'm about to clean up this stuff, and I gotta make sure I put it in a safe place away out of her reach, because she will definitely get in all this mess, and I'll be mortified. I done already had 3 heart attacks today. I don't think I got enough for another.
Well, I guess have a good night.
You too. And remember, y'all, rock truth or nothing at all.